Hi everyone, my name is Debasish and I'm a PhD student at the Institute of Science and Technology Austria, and today I'd like to talk to you about some new mass loss measurements of stars stripped in binary systems. So I'd like to thank Yorick for a beautiful talk and highlighting the importance of stellar winds yesterday. I'd like to begin on a similar note to show you how strongly stellar winds can affect the evolution of a star. Show you this evolutionary tracks here computed using two different wind schemes, and you can very clearly see from this figure that different wind schemes can lead to complete different evolutionary pathway. And this is very important because it can cascade down and affect many things that we can measure and predict. For example, stellar winds can actually affect whether we form a neutron star or a black hole, or what the mass of the final black hole is, what the orbital periods are, the black hole spins, the supernova types. It can affect our population prediction, black hole merger rates, and etc. Let me show you an example. Here I have this metallicity versus the formation rate of merging black holes with three different wind schemes. And as we can see, that three different wind schemes can lead to complete different predictions of our merger rates. So it is very important to use an appropriate mass loss prescription. With this, I'd like to move on from this broad picture of stellar winds to the specific stars that I'm working on. Here is a schematic of how two stars in a binary system can evolve towards forming binary black holes. And during this evolution, they can interact, and which can strip off the outer envelope and form what we call strip stars. Now, these strip stars, although they have been theorized for quite some time, but we only have observed them very recently in the Magellanic Clouds. And since we didn't have observations of these stars, we didn't know what the winds of the stars look like, so the winds of the stars are very uncertain. Now, the points that you see on the HR diagram here, the stars, they have been put on this HR diagram from the optical spectra. But if we want to know more about the wind properties, we need the UV spectrum. So this is because UV spectra contains this classic T-signal lines, which are a signature of stellar winds. And this is how a T-signal line looks like. This is a resonance line. And here I show you earlier study on O-type stars by J.C. Bourret, where he was trying to measure the wind properties of the stars. And this red here is a CMF-GEN model. And these T-signal lines are very interesting because with different parts of these lines, we can measure different wind properties. For example, the edge of this line can be used to measure the velocity at infinity. How strong the emission and absorption components are can be used to measure the mass loss rates. And here I show you why, again, we need the UV. This is from one of my models. Show you a UV line and optical line computed at a certain mass loss rate. And if we increase the mass loss rate here, you can see that the optical line is insensitive towards the changes in the mass loss rate, and the UV line, the nitrogen 51240 line, the more we increase the mass loss rate, the more P-signal like it becomes. You can see all of the optical lines here. The only wind sensitive line here is this helium 24686, and in the UV we have these other two lines. So together these three lines are kind of sensitive towards the mass loss rate, and this nitrogen 1240 is the most important line because it's the most sensitive. And therefore, what I need to do now is to measure the wind properties of the strip star from this new UV observations from HST of the strip stars. And so how we do it? So generally what people do would be to create a grid of spectral models and kind of try to find the fit. Here, so a grid maybe can look like this sometimes, the effective temperature log G and the hydrogen surface abundance, and something similar was done in the optical spectra. But now we have a lot more parameters, and around 11. And if we compute like even 10 models in each direction, we end up with like 100 billion models, which is not computationally feasible. So what we do, use this stellar atmosphere code fast twin and a genetic algorithm. Now, genetic algorithm is a way to probe the parameter space. It works on a principle of genetics and tries to find a good fit of the observed spectra. And since this fast twin code is fast, it makes some simplifications, and therefore we use this more detailed atmosphere code CMFGen to verify our results. So I show you here now my first results of one of the stars, star 2. And on the black, I have the observed spectrum. On the green, I have the best fit with the errors. Here are all the best fit parameters. I'd like to point out this mass loss rate, which is around 10 to the power minus 8.7 solar masses per year. And here I show you the distribution of the parameter space here. This is mass loss rate versus 1 over reduced chi-square. All these points here are one of the models. And we can see that this distribution takes a quite good shape, well peak shape around the best fit model. And this also shows that our mass loss rate measurements are well constrained. This is some comparison with the CMFGen model. And both these codes produce slightly different results, which is expected. But when we speak of the mass loss rates, it's almost similar. So I'd not show you the fits of all of the stars, but I'm showing you the final results here, which is in the luminosity versus the mass loss rate. And there are several trends here we can see. For example, the mass loss rate is increasing with luminosity, and the LMC stars have higher mass loss rate than the SMC stars. And comparing it with the known mass loss prescription that we use, you can see that these are quite lower. For example, star 2 is around 2 orders of magnitude lower. Now this is interesting because these mass loss prescriptions are what we put in our evolutionary codes. And if now the mass loss rate say indeed lower, that could predict a complete different evolutionary picture like I showed you in the first slide. And I show you here a study from Avishai where he computed this the donor star of a binary system. I show you here with two different wind schemes, the Newton-Lemmers and the Wing. And the Newton-Lemmers has stronger wind mass loss rates, so they kind of end up as blue and hot. The Wing scheme has lower mass loss rate, and so it preserves more amount of hydrogen, and which can expand and end up cooler. And now these mass loss rates, which I have measured, are even lower. So it will be interesting to see how it affects our evolution. So for which we would need a new mass loss scheme. So I'd like to mention that this is a work in progress. So I've been trying to find a new mass loss scheme for these strip stars. Can do something like as a function of the luminosity or the metallicity and the helium mass fraction. And just from a simple curve fit, we find something empirical relation like this. And if you want to see how good the fit looks like, here I have the observed mass loss rate that I've measured from my spectra. And on the y-axis, I have the whatever this relation is predicting. And this looks quite good for now. But again, I'd like to mention that this is a work in progress, and I'd also love to have your opinion on this. I'd like to also mention that I've not included one of the stars here because it was a bit outlier. And this is what I need to talk about. I'd like to quickly summarize what I said. So I started with why mass loss rates are important. Then I went on to say why we need the UV spectra. Then I showed you my mass loss measurements from optical UV together. And then finally I showed you my new attempts in constructing a new mass loss prescription. Thank you.
Let's start here.
Thank you. Ling Hao Ma from KITP here. So you're saying the LMC mass loss rate is bigger than SMC. If I'll go back to one of your slides.
Maybe this one.
Oh yeah, this one. Yeah, is that significant? I mean, there's one star in the SMC with very high mass loss rate, right? But that's also at higher luminosity.
Yeah. So, but if you look like diagonally here,
okay.
So this is LMC stars here, and so both the luminosity and the your metallicity could affect how strong is the mass loss rate.
Yeah, but you have metallicities for these stars, right? You have measured. I don't know. You have.
No, these are just I use the LMC and SMC metallicity.
Okay, I see. All right, thank you.
Okay, coming to Tomer.
Thanks, that's really impressive work. I guess I had the same comment. There is one green box, which I think hidden behind it is an SMC star, right?
This is the one which I didn't include in the...
Okay.
Because, yeah, it seems like, I don't know what's going on, so I'm looking more detail into this.
Okay.
So, but yeah, apart from that, in general, the others kind of...
Yeah. And about the mass, the M dot fit that you have there, yeah. I mean, just kind of, I guess, saying what Yorick Vink might be thinking, did you consider including a gamma there, like an L2 over M? Do you have, if you have M estimates or?
So the mass estimates, I have not included mass here because I don't know how good the mass estimates would be from the spectroscopic mass estimates are. So, but yes, I'm looking into it if I can put mass or even other parameters here.
Can put the gamma factor, perhaps. That's a good idea. Okay, that's one.
So just looking at your fit, top background, just looking at your fit, you have some really steep dependencies on the chemical abundances.
Yes.
Do you expect that this relation would hold if you extrapolate all the way to, say, Milky Way?
So recently, actually, I had this, Johanna had found this strip star in the Milky Way. I talked with her that day and I was trying to find if my relation actually could fit into that. And it seemed pretty good, actually. So
okay.
But I don't know because we don't have observations of the Milky Way. So
yeah, so I think this is really potentially interesting. I discussed this with Ilva a little bit already, but at the high end of your range, if you then put another factor of 10 on, you start to get to the point where radio techniques might actually be able to detect these winds, and then you could do stuff in the mid-plane of the galaxy at reasonable distances and not have to worry about the reddening problems. So that might be another way to approach this problem going forward.
Martina Kraszyńska. So I'm obviously thinking about the dependence on metallicity and the fact that, you just separated between SMC and LMC. But is there, so first of all, I should probably know, but are these stars from like similar region in those galaxies or are they spread across the Magellanic Clouds?
I don't know actually about that.
They are spread. Okay, so then the follow-up, is there any hope to get a metallicity estimate that is something more specific to the regions in which those particular stars reside than assuming the Magellanic Clouds seem to have quite a spread in metallicities, and their metallicity distributions overlap for the star-forming population. So this may play quite a role in how you're fitting this dependence.
Yeah, so actually, yeah, for here, for example, I just used the LMC and SMC metallicity, but it would be actually great if we can actually measure from the spectra the metallicity itself. Something I can do.
Yeah, can you or something
I'm not
to
sure. Yeah,
okay,
I'm not sure
thanks.
about this.
I think it's feasible. Sorry.
Kareem El-Badri, Caltech. Have you thought about what the implications of the lower M dots are for other things? So for example, I wondered if maybe it changes the escape of ionizing photons from these stars or the orbital evolution if you put them in a binary.
Yeah, so this will be interesting to see how this affects actually. I have not done that, but this is something I would do here after one of my second project where I would use this to look at how this could affect various stuff.
Thank you.
We can fit one more question if there is more.
So since the mass loss rates are lower, they probably would have some envelope left at the end. So you showed like these stars would expand later on.
Yeah.
So like what types of supernovae would they lead to? Like would it still be like a stripped envelope, or would there be enough hydrogen left that it would look like type 2?
So I think it could be a type 2b supernovae. But if again we have so much mass left, we would again have one more episode of mass transfer. So yeah.
Okay, let's thank Debasish again.